Hey, sorry everyone for my tardiness. I appreciate you waiting around. Um, I'll wait a second to just make sure people are hearing my voice, coming back to the computer, flipping over. But yeah. Um, Kelly, I don't know if you kind of introduced yourself earlier or not, but on this call is Kelly Lancaster, who will be taking over for me for this course starting next week. Yeah, did you introduce yourself at all? Or?
No, not yet. I've been trying to get my daughter set up on her call. But hello. I only see folks' names and cute pets right now, but hopefully I'll get to see some of you guys. Well, I'll be seeing a lot of you in the coming semester, but happy to be with you here today. And I'm just going to observe and kind of get a sense of what you guys have been up to and hopefully try to make their transition smooth and just get to know who you guys are.
All right, thanks. I think it would be helpful for Kelly. I know like a lot of you at least, or most everyone in the class initially at least attended some days face-to-face and some people have been online. I think, as moving forward, it's a good idea for a lot of these kind of Zoom only classes to have your cameras on, just so there's a little bit more of that interaction between people and things like that. Try to have a little bit more of a connection during these things. So, I'd definitely say at least by next week, try making sure you're not showing up in your bathrobe or something like that, right? So you can turn on your cameras or whatever, right? And feel comfortable with that. Kelly, who hasn't never seen you in person and maybe hasn't seen you around campus, might be able to kind of see a look at your pretty faces. So, but yeah. And just to remind people that, right, we're basically the schedule's changing a little bit, right? And next week on Monday will be your exam, and it will cover all of thermo and all of kind of kinetics. And in order to do so, I'll cut a little bit from the kinetics discussions, mainly some, further examples and things like that maybe we won't really get to. Yeah, so we'll wrap up kinetics this week. I posted, right, another homework, a much shorter homework. There's a homework that's due today that hopefully you all have access and should be able to submit on Canvas if you haven't done so already. But there's a homework due today that I'll be grading that. And I see there's already some people have submitted. So just make sure you get that turned in and submitted. And there's another homework that's due a week from today, but again, I made a much smaller homework, and I just want to make sure to have some example problems available for some of the extra kind of kinetic topics that we'll cover this week that are fair game for that exam on Monday. Okay. So before I get going, are there any questions people have about kind of what's happening, the course, or anything like that, or anything related to the homework, anything, just any questions about anything?
So I have a question about the exam. So how do it would look like? It is about the problems or the concepts as well?
So the exam is going to consist of, I actually made it, so I know. It's going to consist of 4 questions. Some have multiple parts. The first 2 questions are a little bit more kind of conceptual, a little bit more about some definitions and other things of that nature. And then the next 2 questions are going to be more like homework questions. I mean, one will be a copy from the homework, at least for this first exam. And then the second, and then the other question will be something new, but similar to homework type questions and things of that nature. And so yeah, that's this exam. Now, not every exam might have as many kind of concept questions and things like that. I guess I'll speak for like how I would do it. Obviously, Kelly, is going to be running the exams and things like that as things go. But how I'd be doing some of the exams after this one is there'll be a few less concepts, because after kind of thermo and kinetics, we get into quantum mechanics, and so we spend more time on the material. The rest of this semester, after this first exam now, is going to be completely quantum mechanics, spectroscopy, all that type of stuff. And so there'll be a lot more time spent on those things. And so it might not be, as many just kind of simple kind of concept questions or something like that. But for the thermodynamics and things like that, I have that on there just because we just covered kind of thermodynamics at such a surface level for a lot of things and very quickly, and some of kinetics. So, but yeah, so for this first exam, that's kind of how the questions are broken down. Give you an idea. And as I mentioned, right, there, at least for this thermodynamics exam, since there's a bunch of, equations that we've covered, how to calculate the enthalpy of a reaction given enthalpies of formations, what's the temperature dependence of vapor pressure of some substance, related with its enthalpy of vaporization or things like that, the temperature dependence of equilibrium constant, the relationship between, oh no, can you still hear me?
Yes.
Okay, my screen like completely messed up. Okay, my screen like did, I wish I could show it on the camera, but it like did some really weird, like it looked like my shirt. There's these green and white stripes everywhere, and it was flashing, and it was freaking out on me. And I don't know, so I apologize for that. But yeah, so I was saying, so there will be a note sheet for this first exam, just because there's just so many random simple equations where like you plug in this equation for the these things into this equation for this problem to try to get the question right. So and it didn't really seem appropriate to try to say, all right, memorize these 30 equations or something. Yeah, it's not quite 30, but maybe close to 20 even equations we've covered in thermodynamics and kinetics for this first exam. And it's not really the purpose of the exam and the course to memorize those equations. So yeah. It will be timed. It will be 60 minutes, so not the full class period for the time for the exam. But I mean, I took it, and whenever I take an exam, I always add extra time on top of how long it takes me, because I already know the questions before taking it, know how I'd want to solve it and things like that. So I always multiply how long it takes me to do the exam by some factor of 2 to 3 or something like that. So, so it shouldn't be like a huge time crunch as well for the 60 minutes to answer those questions. At least hopefully not. So, other questions before we get going here? Problem number 7 in the homework. Explain. Yeah, let me pull up homework here. And I can even share it here. Share screen. What am I trying to share with that guy? All right, so people see the homework here. Yep, okay, nodding. All right, so question number 7, the potential of cell, calculate the solubility product and solubility. Yeah, so some of these homework questions, especially for this class, I just assume some recollection of certain concepts from general chemistry and things like that. So this is assuming you kind of remember things about solubility. If you don't, I apologize, but right. But the idea here, is right for those. Remember, right? So solubility, right, is related with your KSP, right, which is equilibrium constant, right, related. So for example, the solubility product for Bi, that should be underscore 2S3, right? Should be Bi 2S3 here, right? The solubility product for that is related with the equilibrium reaction. You know, oops. Oh, I will drop the annotation here. Bi, what's that? 3 plus. I forgot my stoichiometric coefficient, but there's a 2 here. I apologize. Sorry, I don't have things set up very well on my computer to do this very nicely. And so I'm using my mouse to draw these things instead of like a pen. So I apologize, right? But that's, I don't know if people remember, that should be a 3S2 minus, right? Bi2S3 in equilibrium with 2 Bi 3 plus 3S2 minus, right? Where then, you know, the KSP, right, is the concentration of Bi squared times concentration of S cubed, right? Or S2 minus Bi2 plus, right? You know, equilibrium constants, products over reactants, ratio, stoichiometric coefficients, right? That type of thing, right? And so you know, part of that question is asking, you know, what is this KSP, right? Well, to get at that, we can note the fact that the voltage of any electrochemical reaction, right? Any chemical reaction we have, right? Even if we draw as unidirectional, can go in both directions, right? There's no reason why a reaction, like, I mean, maybe if you're talking about like a nuclear reaction, but even then, technically, maybe you could get it to go in the reverse direction, right? But you know, any chemical reaction, right? You could get to go in the reverse direction. It may be more difficult than in the forward direction, right? That's why often we'll draw certain reactions as unidirectional, because it's very hard to get it to go the other way, right? It's going to require a lot of energy, you know, very high temperatures, or whatever the case may be, right? And so we, you know, but any reaction can be thought of in terms of, it has an equilibrium constant, right? Can be written in two directions, right? So you know, this is the type of reaction that I want in order to get at what this equilibrium constant is. In fact, is any equilibrium constant, the natural log of you know, K, the equilibrium constant, is well, you say proportional, I forget the constants, proportional to the cell potential. Okay. Right, I think it's like the RT divided, no, NF, yeah, that's it. Number of moles times, or number of electrons transferred times Faraday's constant divided by RT. I can try pulling up the slides to show that. Let me do that real quick. Let me find the other slides in Thermodynamics just so I can pull that up instead of trying to recall it off the top of my head. So let's share. So I'm going to share this PowerPoint, right? Go to the very end here. See, there's an Nernst equation. Should be okay. I don't know if I have it written here, but it's right. I have it written somewhere here. Let's see. Should have it somewhere in these slides. Yeah. Here we go. Fantastic. I knew I had it somewhere. Yeah. So, right, this equation here, right? Natural log of equilibrium constants. The number of electrons transferred times Faraday's constant times cell potential divided by RT. Okay. Right. And so the main question is in that problem, right? In the homework problem, how how do I, what is this equation? What is this, you know, this notation here, right? And basically, that notation, it's going to be easier for me to just type this out. Yeah, let me share this other screen. All right, so basically in the notation of bi 2 s3. Oh. Okay. Trying to use shorthand keys here to do superscripts and subscripts, but it keeps on not turning itself off. There we go. BIS 3 solid, right? Bi 2 s3 aqueous. Okay. Right. So basically, the two reactions here, right? This is your shorthand notation for electrochemistry, where you have the oxidation reaction and the reduction reaction, right? So the oxidation reaction is Bi solid, right, going to Bi 2s3 plus 6 electrons. So it should be 2Bi solid, right? And then you have just, you know, the S 2 minus, right? Like the 3s2 minus is just there to balance your reaction, right? So that'd be your balanced oxidation reaction, okay? The reduction reaction that's occurring here, right, is the similar reaction here, okay? But this is, so I'll put, you know, this is aqueous, okay? So I'll, you know, fix that. But the other reaction is literally the reverse reaction. The main difference is one you're forming the solid form, and the other you're forming the aqueous. Right, I need to add the 6 electrons. Okay. Well, this bismuth reaction, right? The aqueous. This is just the Bi. So this is 2 Bi, you know, 3 plus 2 or 3 s, right? Is what that aqueous form is, right? Aqueous forms, it means it's dissolved in solution, so it forms these ions, right? And so that's really kind of aqueous form, okay? And so when you add these two reactions together, right? So when you add these two things together, right, you'll get that the solid bismuth, right, cancels, right? You know, I guess this 3 canceled that, so you're left, right, with your final reaction is this, okay? Which, so this is the overall reaction that's occurring in that electrochemical cell given above, right? Which this reaction, if you think of this as an equilibrium reaction, right? This reaction, the equilibrium constant here is just equal to 1 divided by the KSP, right? And so if I then use the cell potential to solve for the equilibrium constant for this reaction, the inverse of that gives me the KSP reaction, which is again the Bi2S3 solid forming the Bi, 3 plus and the S2 minus. Okay. And so that's how you get at the equilibrium constant. And questions about that? Right. So the main trick here is just to kind of write out what those two half reactions are and what the sum of those reactions give you in order to kind of understand, right, how the overall electrochemical reaction relates with the KSP, that equilibrium constant that we're interested in. Okay. All right. Does that help? Any question on problem 7?
Could you hear me?
Yeah, I hear you now.
Okay. Yes, that helps. But also, I have questions about the cell potential. So we have cell potential. In this case, it's the same as the what is the name?
Electromotive force?
Yes.
Yes. Yeah, cell potential, electromotive force, those are one and the same. Yeah.
Okay, and in this time is the same because we have standard conditions, or is always the same?
Yeah, right, in the slides here, right, I have this little, this funny looking E, right, that's kind of for electromotive force, but it's also referred to as the cell potential for an overall chemical reaction. I'm trying to see if I have written like names for these things, right? Okay, but yeah, yeah, EMF, electromotive force. Yeah, that's referring to the same thing. So I apologize if that was confusing the problem. But yeah, the potential of the cell is the same as the electromotive force for that cell. That's just kind of calling the same thing by two different names.
Okay, thank you so much.
Any other questions?
Can you explain about the power density of cell? Like I did the homework, but I'm not sure whether I did it right or wrong. So can you explain question number 4? I think so.
4. No, power density is question number 3.
Okay.
Sure. Yeah. Don't have to spend too much time. Do you see it now? The questions? Yeah. Okay. Real quick, Jennifer, there will be, so in terms of homework key, I don't have like a detailed solutions, but I do have the answers typed up, and those will be posted after kind of homeworks have been turned in today. Technically, people are able to still submit their homework, and so I haven't uploaded that yet. But once that kind of submission time is closed and everyone's kind of uploaded their homework, I'll post the answer keys to the first homework on campus. So that will be available to you. Yeah, so question 3 here, right? Page 7, 210 Kelvin.
B part, the B part of this question.
Yeah, suppose a biological cell is 10 micrometers in radius. What are the, and there are that many ATP molecules, hydrolytes each second. What's the power density of a cell? So yeah, so the power density, right, right, is how much power per volume, right? And so you're given the radius of a cell, and if you assume just kind of a spherical cell, then you can use that radius, right? What is the? I want to say 4/3 pi r cubed.
Yeah. Yes. That's it.
Yeah. So and it's been forever since I thought about that now. But yeah, so 4/3 pi r cubed, right, to get the volume of the cell. And so that gives you the volume, right? And then it's just what is the total power that's converted, right? And so it tells you hydrolyze 1 × 10⁶ ATP molecules per second. Okay, right? Which earlier in the problem, you'll have, right, that top reaction is the hydrolysis reaction of ATP. So you'll be able to get the free energy change for that reaction.
My question is ATP of cell is equal to free energy?
Yeah, well, so you use, right, so earlier you calculate how much energy you get from hydrolyzing 1 ATP molecule, right? Or per mole, I guess. It's probably per mole, right? Is what you, yeah, these are per mole, right? So you get like the amount of energy, right? The free energy change per mole for hydrolyzing ATP. You can then, figure out, right, obviously how many moles are in 1 × 10⁶ ATP molecules. So you get the, hydrolysis energy, right? The amount of energy you get, right? You can do it one of 2 ways. You can either convert your number of ATPs to number of moles of ATPs, or convert, you know, your final energy per mole for that hydrolysis reaction to like an energy per atom type thing. But either way, that, you know, you do that to basically multiply the number of atoms times how much energy you get per hydrolysis of atom to get the total amount of energy, and that's how much energy is released per second. And so that's that power. So power is energy per time. You know, watts is the joules per second, right? So basically, you should need to calculate how many joules per second are released when you hydrolyze 1 × 10⁶ ATP molecules per second, and then divide that by the total volume in the cell. If that makes sense.
Yeah. I was just confused about if, like, I'm not sure, is it the ATP free energy is equal to the power? So I just want to make sure that that's the point.
Yeah. So right. So right in the problem talks about how the given energy is defined as the maximum amount of work that can be done from the energy released by these type of chemical reactions, right? And so basically you're already given what the free energy change is. You don't even have to calculate it, right? The first part is calculating entropy change, and then that's unrelated to the second part, right? So you're already given how much free energy is given off by that reaction, which is telling you how much energy can be used for work by that reaction, right? So negative 31 kilojoules of energy released means that you have 31 kilojoules of energy, or kilojoules per mole of energy per mole, you know, as this reaction is going, that you can use for work, right? So it's that free energy change that's getting you that amount of, that's related with kind of the amount of power, the amount of work that you can get out of the chemical reaction. Okay.
Yeah, thank you so much.
Mm-hmm. Yep. All right. Let's see. What happened to, lost my, all right. Just, oh, okay, I didn't start it. Let me do that. Let me try sharing that now. All right. I'm sharing the right thing, correct? Or no, here, let me share the slideshow, not my screen. So, okay. So let's jump into kinetics now. So let's see, we talked about first order reactions. Yeah, so we kind of finished off here talking about the temperature dependence of reaction rates, and I was going to talk a little bit about thermodynamics versus kinetic products. So this thermodynamic versus kinetic is in here because last time I taught this course, someone kind of asked about it, so I decided to include just some slides talking a little bit about that. And so we'll kind of just go over that briefly, but you know, this is sort of like an extra topic thing that we won't spend too much time on. But yeah, so let's just go back here, talking about kind of transition state theory and temperature dependence of the rate constant. Okay, so again, hopefully a lot of this stuff is review, but if not, that's fine. Okay, so right, our temperature dependence of our rate constant is related with that Iranian equation, right? And I always forget on these things. Can you see where my mouse is? Or if maybe I can convert my mouse. So you can, okay. I wonder, can I convert my mouse to like a pointer? How do you do that? Spotlight, maybe that. Yes. All right, fantastic. Right. Right, so again, right, you have your Iranian equation, which was originally kind of developed and determined empirically, okay, where they found that this kind of the natural log of the rate constant versus 1 over temperature gave you a straight line, okay, and that gives you this type of equation here. which is A, here's your pre-exponential factor, your Arrhenius constant, as it's also called. It just kind of is whatever it is. We don't worry about too much of that. The main thing here is this exponential dependence on this energy term, EA divided by RT, where EA is the activation energy. Okay. And so, yeah, so, right, this form, right, tells you a couple of things about your rate constants and their temperature dependence, right? The larger the activation energy, the stronger the temperature dependence is on the rate constant, okay? I think I even have a plot, maybe no, okay. Didn't say, I thought I maybe had a plot. I guess I don't have a plot of kind of what that looks like, right? But basically, right, if you have a very small activation energy, okay, or if there's essentially no activation energy, right? Let's say your activation energy, your barrier is almost zero, right? Then your rate's actually gonna have basically no temperature dependence, okay? But if you have a very large activation energy, then any increase in temperature can potentially have a very significant increase in that rate, okay? And we'll talk more about kind of why that is and stuff, but you can get that just from the functional form, right, of the Arrhenius equation here, okay? Right, and if you were to count, measure in lab what the rate constant is for some reaction at two different temperatures, right? You can take the difference of those things to get kind of this equation down here, which is just kind of a direct way that you can calculate that activation energy, basically. So this equation here is often used if you measure in lab, the rate constant at some different temperatures. You can always just use this equation to map out that activation energy. Now, if you're able to do it at enough temperatures, you just make a plot of the natural log of K versus 1 over RT and then find the slope to get the activation energy. But if you're not able to do it at too many temperatures, right, maybe you're limited at the number of temperatures you can really run this experiment at, right, you can always just do something like this, and this will tell you that relationship, right? But you can also use this relationship to calculate, let's say I know what the rate constant is at a certain temperature, I know the activation energy, right? Then I can always calculate what is the rate constant at a different temperature, okay, in order to determine how fast that reaction will speed up if I increase the temperature by a certain amount, right? Okay. Any questions about the Arrhenius equation? Hopefully people have kind of seen that before. Maybe, maybe it's just ringing some bells. Maybe you haven't seen it in a while, but hopefully it's familiar, okay? Right, now where this comes from, one can actually kind of show and derive it from what's called transition state theory, okay? And the main idea in transition state theory is, right, we have some reactant, some product, right, and then there's some type of intermediate state that's related with the lowest energy barrier to get from the reactants to the products, right? And the state at that lowest energy barrier is called the transition state, okay? Right, and so here you have a simple chemical reaction. I always forget if this is SN1 or SN2, but simple chemical reaction, right? Where you're swapping out a bromine, right, for hydride here, okay? And so that transition state ends up being kind of this structure here where you have, this trigonal planar CH3 group, and then the bromine and the oxygen are relatively equally separated from that carbon. So you kind of have this carbon with this kind of weakly dissociated kind of five bonded structure, right? This is what trigonal bipyramidal structure, okay, for this carbon, right? This is not a very stable form of carbon. That's why it's transition state, and that's why it quickly goes either to the products or back to the reactants, depending on what happens when you get there, right? Okay. All right, but the idea behind transition state theory, let me talk about this slide, right? So before we get there, just real quick, the reaction coordinate on these type of plots, right? You'll see plenty of energy diagrams like this in all sorts of different papers, right? And often the reaction coordinate might be some actual bond distance or something like that, but it can be just some general set of coordinates of your atoms and molecules, okay? And so it doesn't necessarily have to be something very, easy to interpret, I guess I should say, right? These reaction coordinates, they sometimes are, but sometimes are kind of these collective motions that don't have a really good representation of, you know, what I could put for the axis, right? Because I could put for this axis, say, the carbon-bromine bond distance, instead of saying reaction coordinate, I could put CBr distance or whatever, right? And that would work just fine for this system, right? But that's not always the case, okay? There's not always a simple bond distance or bond angle or something like that that you can use for your reaction coordinates. Often you'll just see reaction coordinate written down below, and that's just meaning some rough collective motions of reactants and products that get you from the reactant geometry to the product geometry. Okay? So transition state theory basically has kind of two main points to it, saying that, you know, I can have a reaction occur if two criteria are met. Okay? If the reactants end up reaching, if the reactants have enough energy to reach the top of whatever that minimum energy barrier is, right? You know, so in this reaction, right, I have that minimum energy barrier. Do my reactants have enough, you know, let's say kinetic energy, if you will, to get up to this barrier, right? You know, is this oxygen flying in at a fast enough speed to kind of push the hydrogens over and the bromine out in order to get up over this barrier, right? If not, right, if it's coming at a very low speed, it's just going to kind of deflect back off and no reaction is going to occur, right? So I need enough energy to overcome the barrier, okay? And then I also need, the other point is I need the molecules to be oriented in the right direction in order to be able to form that transition state, right? So again, here, if instead of the oxygen approaching carbon, if this thing was flipped around 180 degrees and I had the hydrogen approaching the carbon, right, then no reaction would occur no matter what my energy is, okay? Because the atoms aren't approaching in the right orientation for this reaction to occur, right? For the correct type of bonds to form. And so, yeah, so you need enough energy to overcome that reaction barrier, and you need molecules to collide in the right orientation. And if that's met, then a reaction will form, right? And then you'll form products. And so the kind of question is what is the probability of meeting this criterion, have the right energy? And that probability is given by the Boltzmann distribution of energies. I don't think I had us talk too much about that, and I don't plan on mentioning too much about it. But basically, if you want to know what is kind of the distribution of your molecules, you know, within kinetic energy, what's the distribution of velocities, what's the distribution of, you know, vibrational states in your molecule, what any type of energy distribution, you know, what does it look like? What's the probability of being in certain energy levels at a certain temperature is given by the Boltzmann distribution function, okay? Which is given here. The probability of being at some energy level E alpha, sorry, is e to the minus beta E alpha over Q. You don't need to, you know, memorize this function here. But beta here is just 1 over KT. I think I have that for now, or 1 over RT if you want to use that. But yeah, but so beta is just 1 over the Boltzmann constant times temperature. Q here is this partition function. That doesn't matter. In the end, it gets lumped in with some stuff to form the Arrhenius constant. Okay. But basically, so Boltzmann distribution gives you the probability of having enough energy to overcome the activation barrier, right? I put EA here to indicate that this is the probability of having energy EA, right? And then the rate constant is just going to be related with the probability that you have the energy for the reaction to occur times the frequency in which you're attempting this reaction, right? Which has to do with how often are things colliding, right? How often these molecules colliding together in space, right? That frequency attempt might be limited by diffusion if this thing's occurring in solution, right? Type of a thing, right? And in that case, you can often, depending if that probability of having the right energy is very high, you might get chemical reactions, right? They're diffusion limited. Okay? which is a very common thing that can occur in solutions. You have diffusion of limited chemical reactions, and that's just related with, how often are the reactants able to collide for this reaction to occur. Okay. But that's where kind of this temperature dependence of the Iranian equation comes from this Boltzmann distribution of energy levels. Okay. Or I guess of states within energy levels, right? What's a distribution of molecules within a given energy level? And this will pop up again when you talk about spectroscopy, okay, right? The fact that you don't have just a single peak often for vibrational spectroscopy or electronic or things like that, if there's only a certain energy level, right? So, right, the fact that there's some kind of distribution and things like that occur is partially due to the fact that your molecules aren't all in the same state, right? That they aren't all in the same vibrational state or the same rotational state. This is very important for rotational spectroscopy, where the peak heights in a rotational spectra are pretty much determined based off of this Boltzmann distribution of energy levels. And you can actually use that to back out what the temperatures of your molecule and things like that. So there's a lot of interesting things you can do related to spectroscopy and this Boltzmann distribution and such, but we won't focus too much on it now, but just kind of showing you where this temperature dependence comes from for your Ray constant. Okay, we see it comes from this kind of transition state theory. So questions about the ideas behind transition state theory, what the criteria are required, right? What are the two things I need in transition state theory to occur? Right, for a reaction to occur according to transition state theory. All right, we want to have your molecules collide with enough energy to overcome the activation barrier, and you want your molecules to collide in the right orientation, right, in order to form that transition state geometry, right? Those are the kind of two criteria according to transition state theory for a reaction to occur.
So what is Q in the equation?
Q is called the partition function. Do not worry about it. Like I said, you don't need to know this equation at all for this exam whatsoever. Okay, so don't worry about like the Boltzmann distribution equation. That right. Can you know the idea of what's the Iranian equation, right? But this Boltzmann distribution, what is Q and stuff? Like the functional form of Q is the sum of e to the minus beta times energy levels and stuff like that. But it's not really relevant here. But Q is called the partition function. And just because I say it's not relevant here doesn't mean it isn't relevant to chemistry, but we're just not going to kind of go into that aspect of things. Okay. So yeah. Other questions? All right. So when you talk about, right, so hopefully people have kind of heard of this stuff before, right? Thermodynamic versus kinetic products, right? And so often you potentially have a reaction that has potentially two competing reactions, right? Where they have one reaction has a lower energy barrier, but a higher free energy product, and another reaction has a higher energy barrier, but then a lower free energy product, right? And so we call these, so I'm going to call these two reactions, reaction 1 and 2, as activation barrier 1 and 2, and delta G 1 and 2, right? And so the comparison of those quantities, right, are given here, right? And that's just representing the data that's in this figure. Right? The EA1 is less than EA2, and delta G1 is less than delta G2. So delta G1 is the difference between the product energy and the reactant energy, right? And delta G2 is the difference between the product 2 energy and the reactant energy, right? So that's just a larger gap than this other one, right? Okay. Yeah, right. And so in kind of these kinetic versus thermodynamic products that you see, right? What's happening is, your first reaction, because it has a lower barrier, right, will happen at a faster rate typically. Now that the rate of your reaction doesn't just depend on the rate constant, but it's a good indicator of how fast that reaction is going to be occurring, right? And I should say, not just depend on the rate constant, but it's not just dependent upon the activation energy. But the activation energy can give you a very good indicator as to roughly how fast one reaction will occur with respect to the other, right? So we're just going to assume that these activation energies are really the only main difference between the reactions. So that a smaller activation energy means a faster rate, right? Right, and so when you run this reaction at short times, you'll get a lot of that first product, okay, because it forms just at a faster rate. But, right, as the time goes on in the reaction, that first product is able to go back to the product, or to the reactant, right? Because if it has if any reaction ever has a small activation barrier in the forward direction, right, or smaller, then the reverse direction is going to be smaller, right? So the activation barrier in the reverse direction is larger than the forward, but but that activation barrier, for example, in the reverse direction, maybe is as large as the activation barrier for reaction 2, right? I don't have it drawn out specifically, right? But it could easily be the case, right, that this barrier between product 1 and the transition state TS1, okay, is similar to the barrier between SM and TS2, okay? Which means, right, it is possible to go back, right? And so you will start to have P1 going back to the reactants, and eventually you'll establish some type of equilibrium between the reactants and P1, right? And because of the fact of the difference in these activation energies and the free energies, right? We also know the fact that since the free energy is lower for P2, okay, the activation, or the equilibrium constant to K2 has to be greater than K1, right? So at equilibrium, I have more products P2 than I do P1 based off these equilibrium constants, right? And so, right, what's happening is P1 quickly establishes equilibrium with your reactants, and then you start forming reactants back. But then when you form the reactants back, again, that reaction could go back and form P1, but the reactants can also then go and form P2, right? And so, but P2, it takes a lot more to go back to the reactants because of that larger activation barrier, right? Right, there's a lower free energy and a larger barrier. So that reverse barrier is extremely large, right? And so eventually, right, over time, even though you get more P1 initially, the concentration of P1, if you were to monitor that in a system like this, will slowly decrease over time until you get mainly P2 products, right? Right, and so that's what these thermodynamic versus kinetic products is related with, right? And the kinetic product, if you mainly want that, you got to stop your reaction fairly quickly, right? While the thermodynamic product, you got to keep it running because you want basically the equilibrium to be established between P1 and your reactant, so that P1 can start going back to form reactant, so you have more chances for the reactant to form P2, right? And the idea is once you form P2, you're effectively stuck at that P2. Okay. So questions about thermodynamic versus kinetic products?
So this is about same reaction with different product?
Yeah, so same reactants with different product. Yeah.
Okay.
Yeah.
So what if there is a catalyst?
So so it could be yeah. So if you happen to have a catalyst that lowered TS2 below TS1, right, for example, but you have the same P2, right, then that would just make it so your kinetic and thermodynamic product are the same thing, right? You know, so the kinetic product and the thermodynamic product can be the same thing depending on, you know, if the activation barrier is smaller and the free energy is smaller for a certain product. Okay, and so yeah, so adding a catalyst to this reaction, assuming it doesn't affect what the potential products are formed, right, can either just make this kinetic product, the green curve, even faster, or it could end up making the thermodynamic product, the blue curve, also the kinetic product if you're able to lower the activation barrier enough. Does that kind of answer that question?
Thank you.
So is this affected by the relative difference in activation energies and free energy, or is it general? Right. So I'm just looking at the question in chat here. Right. It does matter if you have a very small difference in activation energies but a large difference in free energies, that can be very relevant, right? So kind of how much P1 is favored in the short time and how much P2 is favored in the long time, right? Very much just depends on how big of a difference these activation energies are and these free energies are. Okay? And so yeah, so the relative difference does matter in terms of, this type of system, something like this occurring, okay? Because if these relative differences are pretty small, then it might actually, then it might be that you could not get equal contributions of P1, right? Let's say the difference between EA1 and EA2 and delta G1 and delta G2 are very small, right? Then it could be that you get, maybe close to a 50-50 mixture of the two products by the end of your reaction, right? Right. If they were exactly the same activation barriers and exactly the same free energies, right, then it would be a complete 50-50% mixture of the two products. Now, that's not going to be the case if they're exactly the same, right? But yeah, that can affect things, right? If the activation energies are very similar, but the free energies are very different, right? Then, your kind of kinetic product would be both P1 and P2, but then your thermodynamic product would still be kind of P2, right? Where as you're forming P2, it gets trapped and stays there while in a short time scale and very high temperatures, right? You can form both P1 and P2 at relative equal rates, assuming, say, the activation energy is almost the same between the two, right? So yeah, so that it very much depends. All right. Okay, so let's start talking today about reaction mechanisms, and we'll spend the rest of the time on Wednesday talking about reaction mechanisms. Okay. So just introducing the idea of mechanisms. Okay, right. I guess real quick, is there anyone here that hasn't really, gone over reaction mechanisms before in their classes or things like that, doesn't really remember what is a reaction mechanism in elementary step, what are those definitions and things like that? What's an intermediate? What's a catalyst? Anyone? Okay. I don't see any comments or anything like that, right? So just right. Right, a reaction mechanism, right, is a sum of different elementary reactions, right? An elementary reaction describes how things are actually reacting, okay? Right, like O colliding with NO, colliding with N2 to form NO2, sorry, to form NO2 plus N2, right? Well, general chemical reaction, right, doesn't necessarily describe how things are reacting, right? I don't have an example. Where's the example, right? Oh, what happened? What? Why are those slides blink? Huh? Second, I don't understand what's going on here. Is there a formatting issue? Give me a second. I don't understand why. Why is it weird on me? Let me, I think I pulled up. Let me pull up something real quick here. Let me pull up the PDF. I don't know what's going on with my PowerPoint. It's not.
You can use the Canvas one because we have those ones.
Yeah. So I'm pulling up the PDF that's in Canvas. That's what I'm doing. I'll share that screen in a second. I don't know what happened with my PowerPoint here as to why the images aren't loading properly from this computer. It shouldn't be that problem, but okay. So hopefully, right, you see the PDF. Okay, fantastic. Yeah, right. And so we have intermediates, right, and things like that, which are something that's formed and then consumed within a reaction mechanism that doesn't appear in the overall chemical reaction, right? So if you had, I'm trying to see if I'm just a random example of an overall chemical reaction, not really fantastic. Right, but like the reaction H2 plus Br2 forming 2HBr, right? That reaction is just a chemical reaction and does not necessarily describe how things are actually colliding, okay? And so reaction mechanisms describe how things are colliding, what bonds are being formed and deformed and things of that nature, okay? And so, right, so in these mechanisms, right, you can often have intermediates, which are something that appears in the reaction mechanism but doesn't appear in the overall chemical reaction, right? And then the rate laws for elementary reactions can be written directly based off of the reaction itself, right? Because this reaction is H plus Br2 forming HBr plus Br, right? And it's talking about the collision of these two molecules in order to form the product, okay? The rate of this reaction, the rate law, is just given by the rate constant of that reaction times the concentration of the reactants, okay? Right? Which happens to also be related with the rate of change in those concentrations, right? Because of the fact, right, by definition, right, the rate of the reaction is by definition related with negative dH dt, negative Br2 dt. It's also related with positive d HBr dt and dBr dt, right? Okay. So, right, so questions about kind of, again, what is a reaction mechanism? What are elementary reactions, intermediates? Why the rate law is what it is for this elementary reaction? Any questions about this stuff? I kind of breezed over it just because it should hopefully be things that are familiar, but if it's not, that's fine. If things aren't familiar, that's fine. I'm happy to spend more time talking about these concepts, but yeah, so what I'll do is I'll just keep going. If ever you want me to expand more on something, just let me know, and I'm happy to take the time to do so, right? And so what's important for us to do often with these mechanisms is relate, based off these elementary steps, right? What are the rate of changes of concentrations of different reactants products, and thus our rate law for a reaction given the mechanism, okay? So for example, right, in this reaction, I want to know what is the rate of change in the concentration of B as a function of time, okay? Well, in that first reaction, right, B is being produced, so its concentration should increase with time, and it increases at the same rate, right? Okay, that this increases at the same rate as, I'll call it, say, V1, right? The rate of reaction 1, right? This reaction 1 has some rate that corresponds to the rate law, K1, right? Concentration A squared, right? Right, so that first reaction is causing B to be formed at the rate in which that first reaction is occurring, which happens to have a rate law equal to K1A squared, right? In the second reaction, B is being consumed. It's being consumed at minus the rate of that reaction, V2, if you will, which happens to be the rate law for the second reaction is, rate of that second reaction equals K2 times concentration of B times concentration of D, which is what that is, right? So the total change of the concentration of B as a function of time, right, is then just a sum of those two changes, right? Just K1 A squared minus K2 B D. Okay. So questions about how I got this on this slide? All right. If this isn't familiar to you, if it doesn't make sense, please say something, because when we talk about mechanisms, we're going to be doing this a lot, right? We're going to be relating these elementary steps with the rate laws and talking about rates of changes of certain reactants and products and the overall rates of our reactions. Okay. In order, right? The goal is, right, if we propose a mechanism to solve for the rate law given that mechanism, and then compare that rate law to the experimental determined rate law, right? Because that's what you would do in lab, right? In lab, you'd propose a mechanism, you'd solve for the rate law of that mechanism, and then you'd say, does that agree with my observed observations in terms of rate laws and concentration dependence of my rate laws and things like that. Okay. All right.
Sorry, I'm confused about the negative sign.
Yeah, so the negative sign is here because in the second reaction, B is a reactant, which means it's being consumed. So its concentration is decreasing over time, and so its concentration, and so that's why that minus sign needs to be there.
Okay, thank you.
All right, right. Let me clear the drawings here. Right. If I have an equilibrium reaction, right, then that's effectively just two reactions going on, right? So this top reaction here is effectively 2A going to B and B going to 2A with rate constants K1 and K minus 1 respectively, right? And so, right, given this mechanism, right, these would be the different rates of changes of my reactants and products and intermediates in this overall mechanism. Okay. Right. Again, this is an example of something that hope, you know, that all four of these equations should make sense. How I got them, where they came from, in every way, signs and everything. So if there are questions about this, oh shoot, there is a mistake here. I need to correct it. It should be like A squared and A squared. So I know there's that mistake. This should be A squared. That should be A squared. But yeah, so I'll have to fix that on the slides. Any questions besides the missing squared there? So we don't have the coefficients. Yeah, so these coefficients only appear, right? So the coefficient 2 here in this reaction only matters for the change in concentration of A. Because basically what we're doing in these reactions, right, is I'm relating the rate of change. Let's say dB dt, right? dB dt is related with minus V minus 1, right? The rate of that reverse reaction, okay, plus V1 plus, sorry, not plus, right here, it'd be minus V2. Okay. Right, and the idea here again is the rate of change of B is related with how fast B is being consumed in the first reaction, okay, which is negative V minus 1. How fast B is being produced in the forward direction, which is just V1, the rate of that forward reaction, and then how fast B is being consumed in the second reaction, right? So why there's a factor of 2 that appears here, right, is because in this first reaction, A is being consumed in the forward direction, right? So there should be a minus, and so it should be V, right, minus V1. But every time this reaction proceeds at like 1 mole, right? Every time I form 1 mole of B, I got to consume 2 moles of A, right? And so the rate of the reaction, right, is going to be half the speed of the rate of change of A, right? Or another way to say that is, right, the change of concentration of A is 2 times faster than the rate of the overall reaction because that's stoichiometric coefficient of 2. And so I have to multiply by 2 here, right, to get 2 times the rate of that forward reaction is how fast the concentration of A is changing over time. Okay. Right. And so the 2 appears only in the relationship between the change in A as a function of time when A has some sort of stoichiometric coefficient on there. Okay. Right. And again, B, it doesn't appear because there's no stoichiometric coefficient of 2 here for B. So I don't get, 2K1A squared. Instead, I just get K1A squared. Right. That should be squared. Other questions? All right. So just note here, right, that if you have these equilibrium steps, okay, even if your reaction's at equilibrium, that does not mean the rate constant's equal, right? Right. If you recall, a chemical reaction at equilibrium is when the forward rate equals the reverse rate, right? And so the forward rate is K1A, the reverse rate is K minus 1B, okay? And so, right, what that means is A squared. I have, that A squared issue followed here. So that should be A squared, this should be A squared, this should be A squared, and this should be A squared. Right. Right. But the main rate, meaning, right, again, the rate of the forward reaction is equal to the reverse. Okay. And so, I know the rate laws for the forward and reverse reaction. I set those equal. Okay. And what I get is this relationship here. K1 over K minus 1 happens to equal B over A squared. Okay. Well, B divided by A squared happens to also be, by definition, the equilibrium constant for this equilibrium reaction, right? Which just shows you the fact that the ratio of K1 over K minus 1, the rate constant happens to equal the equilibrium constant for that equilibrium reaction, okay? And so, yeah, so saying a reaction is at equilibrium, right, means your concentrations obey that equilibrium constant kind of expression, right? And that equilibrium constant, again, happens to equal K1 over K minus 1. All right. So I think what we're going to do is we're going to skip these slides. So basically, some of these slides here is just kind of showing, if we were to actually solve for the concentration dependence as a function of time of all these things, it's kind of annoying and difficult. You got to do some different integrations and then solve some differential equations and blah, 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 right? To get just kind of this exponential dependence of A, this exponential kind of roughly growth of P, and then the intermediate grows and then decays kind of exponentially, right? And again, the mechanism, right, is just reactant A going to intermediate I going to product P. So very simple mechanism, okay? But it can give you kind of annoying solutions to the concentration, say, as a function of time. And so we don't want to do this in general. And so we make approximations when trying to solve for our rate laws and our concentrations over time. And one of these approximations is the steady state approximation, okay? And the steady state approximation, right, basically, right, so again, the idea here is, if I solve this exactly, I got these funky looking expressions, right? In general, I can't even, if my mechanism is any more complicated than this, getting these answers potentially becomes almost impossible, to where you need to just like numerically solve for certain things by running simulations and evolving your simulation over time, right? Or we need to use some type of approximation. And so the first approximation that we're going to talk about is the steady state approximation, okay? And the steady state approximation just basically assumes that after you form some initial amount of your intermediate, that the concentration of the intermediate as a function of time does not change, okay? That I don't have a situation like what's on this figure here, but instead what happens is my concentration increases for the intermediate, and then it stays relatively small and relatively constant until kind of the end of the reaction where it dies off and goes away. Okay. And so yeah, and so that's kind of what the steady state approximation is getting at, is that change concentration of I as a function of time equals 0. Okay. If I apply the steady state approximation to this simple mechanism, okay, I get this formula here, right? The change concentration of I as a function of time happens to equal Ka times concentration of A. That's how I is being formed. And then it's minus Kb times concentration of I, right? I, again, is your intermediate, right? So if I want to know what is the concentration of my intermediate as a function of time, well, it's just related with Ka divided by Kb times concentration of A, right? And so for this approximation to be valid, the concentration of I needs to be very small, which means Kb needs to be much, much larger than A. Okay. So for the steady state approximation to hold true, the second reaction has to be much, much faster than the first reaction. Okay. And that should make sense, right? Because if my second reaction is very fast, in an intermediate that I form, I almost immediately use up, right? And so the concentration of the intermediate should be very, very small as my reaction is taking place, okay? I'm relatively unchanging because I'm consuming it as fast as I produce it, okay? Right. And then, you know, getting the change concentration of the products of function times end up being a little bit easier using things like the steady state approximation, right? Because using the steady state approximation, I can substitute in for I, Ka divided by Kb times A. That then simplifies to just Ka times concentration of A. Okay. All right, so examples about what the steady state approximation is. I know we're just basically about out of time, but questions, or sorry, I said example. I mean, questions about what is steady state approximation, okay.
So why do we need the steady state approximation? Can you explain it a little more?
Yeah. So why we need it is if I have, let's say I have, you know, a mechanism like this, and I want to know what is the rate law. Okay. Well, the rate law for this mechanism, right? The rate law is just related to the rate of the reaction, right? The rate of the reaction, okay, which the rate of the reaction can be written by relating, say, the rate of change in the concentration of P as a function of time. Okay. By definition, right, for my overall reaction is just A going to P, right? So for my overall reaction, A going to P, right, by definition, the rate of the reaction is dP dt, or say minus dA dt, right? Either way, you know. And so, so my rate of the reaction, for example, is related with dP dt. So P there, right? Well, based off of my mechanism that I'm proposing, dP dt just equals Kb times concentration of I, okay? Right? Now the problem is I here is an intermediate, so I can't stop here and say, okay, this is my rate law, right? My rate law for this overall chemical reaction is predicted to be just Kb times I, right? Well, you know, if I'm running an experiment, I'm going to tell you, you know, figure something else out because I can't measure the concentration of I, right? Especially if this steady state approximation holds, right? And the concentration of I is very, very small and fleeting, right? Measuring it accurately as a function of time isn't going to help me in terms of knowing what the rate of my reaction is and things of that nature, right? And so I want to get rid of that concentration dependence on the intermediate, okay? And basically without making any approximations, that becomes very, very difficult to do. It is possible for this reaction mechanism, but in general, it's not necessarily possible. So we need to use some type of approximations in order to remove the rate law dependence on intermediates, okay? And that's where the steady state approximation comes in, right? The steady state approximation tells you, is saying the concentration of I is a function of time, right? Its change is equal to 0, okay? And this often produces some set of equations like this one here that relates to the concentration of your intermediate I with the concentration of a reactant A. And so I can, then plug in, solve for I in terms of A, right? And then plug this in to my rate law up here, right? To get a new rate law of the reaction, which is the rate of the reaction equals Ka times concentration of A, right? Which is a valid expression because A is a reactant. Okay, so we need these steady state approximations, and then the pre-equilibrium approximation we'll talk about at the beginning of class next time on Wednesday, in order to kind of get rid of intermediates in our rate laws, to get something, and to get our rate laws in terms of things that we can actively measure potentially in the reaction. Does that kind of make sense? Does that answer your question, I guess I should say?
Yeah, thank you so much.
All right. Well, I don't want to go over time. I know we started a few minutes late. I apologize about that, but I also don't want to take up extra of your time. So we'll end here. What we'll do, so I'll just quickly talk about it, right? So we'll finish kinetics on Wednesday, and what we'll do is we'll go through an example, probably just this kind of simple O3 example here. I have this complicated rate law with the answer written here that you can go over yourself and kind of figure out. But we'll do this example, and then we'll talk about the rate determining step, pre-equilibrium approximation, and then we'll do. I think we'll talk about enzyme kinetics. I think it's something useful. And assuming we have time, and I hope we do, we'll talk some about photochemistry. Kind of, I want to do some examples as well as talk about concepts of photochemistry and enzyme kinetics. So I think those are the kind of most relevant things often for things that you're doing. Okay. But I don't know if we'll get to kind of polymerization reactions or discussion of inhibitors and things like that. But these slides are here, and you're welcome to read in more about this stuff if you're interested. And I'm happy to talk to you kind of one-on-one about some of this stuff as well, if you'd like. But so that's kind of the plan for Wednesday. Okay. Any other kind of questions before end of the meeting? All right, well, I will see you guys on Wednesday. Again, the homework, it might be closed now. If you didn't submit your homework and you're not able to submit it still, just shoot me an email with it this time around. But try to get it in. I guess the window. I think the window typically ends at the end of class period, because the idea was people turning in their homework in person would turn in their homework by the end of class period. And so if you're online, you have to turn it in by the end of class period. Now, maybe with everything being completely online, the due times might change, and you can always talk with the new faculty about that as well. But yeah.
Yeah, happy to take suggestions for things that have been working well for folks online and make things as easy as possible. But thanks for letting me sit in. Nice to meet everyone.
All right, well, I will see you guys Wednesday. Okay, have a wonderful rest of your day.